In this session, let's look at the process of graduation and the various statistical tests that are used for testing out the graduated rates. So what do you mean by graduation first of all? So in the context of insurance premium settings and aspects relating to mortality rates, when we define graduation, it's more of a process of smoothing the mortality rates data. A process of smoothing the mortality rates data. I collect the mortality rates from the real world observation. I'm investigating, let's say, a set of people, a big, huge sample of people at different age groups. Let's say X, X plus 1, X plus 2, and so on. So I'm looking at a large sample of people in each of the age categories and how many of them have died within each of the age category. So from there, I'm trying to get an estimate of the mortality rate out of the number of people who are observed in each of the red category or in the each of the age category. So I'm trying to find out what is the proportion of people who have died during the observed period, like generally a 1 year kind of period. And based on what the mortality rate out of let's say out of n people who have observed, 2% of them have died within the age equal to x out of the n people who have observed. So those people have died within the next 1 year. 2% of them have died whose age was equal to x. Now, like that, for each age category, I separate the estimate of the mortality rate. That particular estimate of the mortality rate obtained from the real world observation from the data, we are calling that as screwed mortality. With respect to this screwed mortality, there could be some kind of problem where the values will not be smooth over the ages. Probably it may so happen that probably during the observation period, people with the age 20 may have died more than the age 21, or the age 22 would have numbers would have been lesser, or the proportion would have been lesser. Now, how do I justify that people with 21 people have died with compared to 20 or 22? So we need to understand with the age, the mortality rate can keep increasing with most of the ages. As the age is increasing, we see that the mortality rate can keep increasing. But when I use the crude mortality as the case, it might be very well possible that the mortality rates are not smooth, which means the premiums which I'm trying to design based on the mortality rate, it may so happen that I may charge a higher premium for a 20-year-old person, or lower or higher for a 21, or higher for a 21, or lower for a 22. So a person with a higher insurance premium will not be able to get this one for the 21, but you select for this one which is with the lower. So I cannot create a satisfactory explanation if the rates are not smooth. So graduation, with whatever we're doing, the key intention is you take the initial crude mortality rates and you apply some statistical technique, so that there are two cases. We have two cases so that we have the rates which are smooth and at the same time adhere closely to the crude data. Not too much deviation from the crude, but close to the crude observed. So the major intention is to smoothen the mortality rates and try to reduce the error because of the sample that has been collected. So we try to reduce the sampling error to whatever extent possible. So we are trying to reduce the sampling error to a large extent possible. So as the ages are increasing, the mortality also keeps increasing, and vice versa. But always remember, when I trying to produce a extremely smooth is just like a pattern with the edge. So if I try to produce a smooth data, adherence to reality may be a difficulty. So if we move to more adherence, then the smoothest is a problem. So basically, this is just like a trade-off. It's a trade-off of smoothness to the adherence of the actual data. So I have to announce some adjustment to the data. So it has to look like a better graduation process, which has to balance the smoothness and the actual data. So the main intention of this process, we have a notion saying as age increases, we see that the mortality, the number of people dying during a particular period, should be higher than compared to the lower age group. So at least pay a greater number of ages, like a maximum set of ages, a maximum kind of setup is going to be created. And at the same time, if I'm designing the premium for insurance policies based on these mortality rates, I will not be able to justify why the premium for a 21-year-old person for a 20-year-old person should be low, 21 should be higher, 22 should be lower. So why should that happen? That is something that cannot be justified in the real world. So it's better to smoothen the rates, right? Unless there's some kind of association that can really be thought of, it cannot be justified. So that is one of the prime reasons why we do the smoothening of the crude rates, so as to explain these aspects comfortably and to make the pricing of the products quite effectively. So now I can look out for the distributions for the number of deaths. So now I'm going to look at the distribution for the number of deaths. So I can create a distribution for the number of deaths. So one way I can assume that the number of deaths follow a Poisson distribution. So I'm trying to create the distribution to smoothen out based on the accrued rates. I'm trying to find out a distribution for the number of deaths. So if I'm assuming a Poisson model, so I can very well see that the distribution for number of deaths at the age x is following a Poisson distribution. The lambda here I'm taking is the total exposed to risk. For this age x, I'm multiplying it by the mu x plus 1 over 2. So this means that the typical the force of mortality, I'm taking the force of mortality at age x plus half, and that particular force of mortality, I'm multiplying it with the total central exposed to risk at that particular age x. That is what is giving me the distribution of death for a Poisson distribution, if I'm assuming the deaths are following a Poisson distribution. So if the exposed to risk is very large, then I can very well assume to follow a normal distribution, which the Poisson distribution approximates to a Poisson distribution approximates to a normal distribution with the mean, which is central exposed to risk, and so this is the mean, and the variance is also the same, mu x plus 1 over 2. So this is the central limit theorem assumption. So the Poisson distribution will approximate to the normal distribution. So if I'm assuming that the deaths are following a Poisson distribution, I can model the death for the age x as a Poisson distribution, as the lambda as the center exposed to risk, and multiply by the force of mortality at the age x plus half. But if I'm assuming that the deaths are following a binomial distribution, a binomial model, then we use the same logic. So the deaths, which is the x, are following a binomial distribution with the exposed to risk exc as the number, and I'll take the probability of death within the next 1 year. So this is the discrete probability of death within the next 1 year. So this is the model for the death. Okay. So if the EX is also very large, the binomial distribution will get approximate to the normal distribution with the mean of EX, which is exposed to risk, multiplied by QX, and then the variance with exposed to risk multiplied by QX, then multiplied by 1 minus QX. Because the mean of the binomial distribution is NP and the variance of the binomial is NPQ, or NP 1 minus P. So it's also the same for the normal distribution as well. So whether the deaths are following the binomial distribution or a Poisson distribution, and depending on whether the exposed to risk is very large number or a small number, I will use that distribution on an approximation. Okay. So I'll use this to identify the smoothing of the numbers with respect to the death rates. So why do we need to do all these things? Whether it's finding out the distribution or smoothing out. So you see, what typically happens is at different points in time, I may want to use a comparison analysis. So comparison between various products. What has been there? What has been the death experience with products, or death experience over time? So we need to find the comparison between the two, or I would like to compare some actual with a standard tables presented. So we have two forms of standard tables. So we are looking at tables prepared by the national data. So these are national life tables. These take the census data and the death registration across the country, whether the person has insurance or no insurance. This data is purely taken from the population, from males, females, census related data, or the death registration which have occurred during a particular period. And these are based on the mortality rates. Okay, so this is one set of table, and the second set of table are the data based on insurance companies. So whatever has been provided by the insurance company with respect to the mortality experience. So based on the number of policies, number of deaths which have occurred between the period, they create this kind of table based on whatever has happened. So these are something like these are some of the two standard tables which we can have. Okay, so on this side we can have the ELT15, and then on the other side we can have AM92 from our actual tables. Okay, so you can find this from, if you see in the actual table, we have the ELT15 and the AM92. Okay, so this help us to understand if there has been any kind of difference between the different kind of products. Okay, so if there is any difference in the actual calculation or actual values compared to the table related values, all these things or all these comparisons are helping the insurance companies to make the necessary modification to the pricing experiences. So that is why some of the consistencies we like to check out in this process is, so whatever my observed rates are the observed rates consistent with respect to standard table. So here I could have taken the AM92 or EL15, or I want to test out whether the observed mortality rate at each age are consistent with respect to the standard tables, depending on whether I'm going on a discrete node. I'll use QX, otherwise I'm taking UX plus half. So from my standard table, I'm considering this kind of values and I'm taking the observed. So I'm doing a statistical test with an I hypothesis saying, so I'm saying for the real mortality rates for each age X, rates at each age are equal to are equal to the rest determined by the standard tables. Whether it's qx or nu x plus half, there is a consistency between them. Sometimes we like to test out the fitness, the actuals to the graduates. If so, I may look at it with respect to. So these are standard table for S, QX. This is standard table. So if I'm comparing it with graduated rates at each edge is equal to graduated rates. So graduated rates are denoted by QX with a circle or nu x with a circle. So this is a comparison with the graduated rates. And then this other one is a comparison with the standard tables. So the second one is a comparison with the graduated rates. So I can compare the observed rate. So I can compare it with the standard table, or I can compare it with the graduated rates. Again, I can compare these two to see if my experience is consistent with the two. So whenever we're doing any graduation, we know that it's a trade-off between the smoothness and adherence to the reality. At the same time, we're also thinking about the suitability for the process. So here we have to determine the premium. We have to determine the premium so that they can be smooth. Okay. So people at some age levels may not even take the insurance policy. So apart from maintaining a trade-off between the smoothness and the reality, I will also be looking at the suitability for a particular purpose. So when I'm trying to compare the actual mortalities with respect to the graduation, comparing the actual mortality with respect to graduation, especially when I'm using let's say if I'm using a Poisson model, I can use the graduated distribution as a Poisson model. I can use the graduated distribution as a Poisson model. So I want to compare under the assumption that the deaths follow a Poisson distribution with the center exposed to risk multiplied by graduated nu x plus half, or the death will approximately follow a normal distribution with center exposed to risk nu x plus half, which is graduated, and the variance, which is also being center exposed to risk, which is graduated. So if at all I'm using a Poisson model where I'm trying to express the force of mortality at age x plus half, but if I'm going with a binomial model, again the same, the dx will follow a binomial distribution with initial exposed to risk and qx, which is a graduated qx. Or when ex is very, very large, then I'm assuming it will follow a normal distribution with a mean as ex, qx, and variance as ex, QX 1 minus QX, a graduated rate. So these are graduated rates. So using the central limit theorem, but the only thing, whether it's QX or nu x plus half, I'm considering these graduated rates and then using the Poisson distribution model and then trying to compare it with the actuals. So here comes the various tests. So the various tests are, so the first test is test for smoothness. Test for smoothness in the data. So whatever the distribution we're using for the graduation purpose, the best way to test for smoothness is you take the third difference. Whatever model you're using, you take the third difference of the graduated rates. When I say a third difference, so let's say 30, 31, 32, 33, up to 40. So I got some graduated rates A, B, C, D, and so on up to K. So these are the set of graduated rates. So I call this nu x plus 1 over 2. Okay, so these are the graduated rates. So based on the graduation model which I've used, whether it's a Poisson model I've used, based on the Poisson model which I've used, I got the graduated rates like this. Okay, so if I'm saying third difference, so the first difference is delta. So in this case, when I'm trying to compute the first difference delta, this is what A minus B, B minus C. This is the first difference. This is C minus D. So these are the first differences. Then similarly, I'm trying to get the second and the third. That is the way I'm trying to find the third differences. So you can write it as B minus A, C minus B, D minus C. Similarly, I'm taking delta squared, C minus B minus of B minus A, D minus C minus C minus B. So the delta is coming out as, so this one is coming out as C plus A minus 2B. So this is the second difference. It's also kind of D plus B minus 2C. And the third difference, I'm getting D plus B minus 2C minus C plus A minus 2B. So this is coming out as minus D plus 3B minus 3C minus A. So this is what we call the third difference. So every 4 rates, if I found out there is D plus 3B minus 3C minus A, this is what I call the third difference. In case of this third difference, if the third difference values are very, very small with respect to the original graduated values, the third difference value are very small with respect to the original, then we say that this particular graduated rates are very smooth. At the same time, the third differences graduate the progress regularly with age. As age is increasing, you see that the third difference is also increasing. So the important test with respect to testing for the graduation is the third difference should be much, much small when I compare them with the original graduated rates. and along with them being small, they should increase gradually with respect to age. When these two things are happening, we can very well say that this particular graduated rates are more and more smoother. Okay, so that is one important test we can use for the testing of the smoothness of the graduated rates, right? Okay, now we have to look out for testing for adherence. So this is for testing for the smoothness of the data. So the next thing we're going to look out for is the testing for adherence. Test for adherence to actual. So this is the second test to the actual data. First one I'll look at is the standardized deviation. So depending on whether I'm using my graduates are whether I've used the Poisson distribution to estimate the graduated rates or a binomial distribution to estimate the graduated rates QS0, I will be using a standardized deviations test. So for the standardized deviation test, I'm looking at for each age, I'm looking out for the actual number of deaths. So these are the observed minus the expected number of deaths using the Poisson distribution model or the more normal approximation of the. I take the central exposure risk, I multiply by nu x plus half graduated and divided by the standard deviation. We know that the variance is central exposure risk if it's following a Poisson distribution. The mean and the variance are the same, which is the central exposure risk multiplied by the forced mortality at age x plus half. So as part of the z computation, so we say x minus nu by sigma. So this is going as the actual observed number of deaths minus the expected number of deaths divided by the standard deviation by the number of deaths. So this is under the assumption that it follows that the deaths are following a Poisson distribution, and I have graduated the rates using the Poisson distribution model. So this is what we are using for testing out whether the graduated rates are adhering to the actual data or not. Similarly, when I'm going with the estimation of QX based on the binomial distribution model, the ZX again becomes being comparison of the death at age x with respect to the mean of the binomial distribution, normal approximation of binomial. So the mean is the exposure to risk multiplied by graduated QX, and the variance is exposure to risk multiplied by QX multiplied by 1 minus QX. Alright, so this is the variance, so I put the square root to give me the standard deviation. So I'll look at it with respect to normal distribution. I will compare these with respect to normal distribution to compute the z. So I compute the z at each of these aspects by computing the standardized deviations, and based on this z that gets created for each of the age x, for each of the ages, to see whether my data, whether my observed data fits the graduated rates. graduated rates. So I'm using a chi-square test to test if my actual data is fitting the observed data. I'm using the chi-square. So I'm defining the chi-square as the summation of the zx squared. Okay, so the chi-square is the summation of the zx squared. So whatever this is, I'm comparing. Whatever I get here, I'm comparing it with the chi-square distribution. And how many degrees of freedom I have to use? So every comparison I have to use the degrees of freedom. I have to find out the degrees of freedom I'm using. So generally, it depends on the kind of graduation model that is being used, right? Yeah. So depending on the degrees of freedom that are being used, we will try to look at for depending on the model that is being used for the graduation purpose, we will use the degrees of freedom accordingly. So our calculated values are compared with the chi-square values. Okay, so if the calculated values are much more than the calculated values, then we can say we can reject the null hypothesis. So from here we can do the you can do the calculations, and you can find out how to reject, whether reject or accept the null hypothesis. Okay, so this is how the standardized deviation test for the actual difference is done. Okay, yes. So you can have the test at 95 or 99%, and we can say that the graduated rates are much deviated from the observed rates. So the chi-square test, whatever we are using here, it's a Y-tail test because I'm more bothered about only on the higher side. Okay, so if I'm looking at the chi-square, so as long as my zx square is not greater than this particular value, I am not rejecting the null hypothesis. Only if zx squared is greater than, if it's lesser than, I'm not bothered much. So if the larger the values of the test, then only I'm confusing that the observed are quite different from the expected, which I calculated using the graduated rate mechanism. So that is where if the only observed zx squared are very much higher than the critical value, then I would be rejecting the null hypothesis, and based on that I'll be concluding that the observed number of the actual depth experience is much different from the expected number of which are computed using the graduated mechanism. But in this model, using the chi-square and finding out the individual zx and then squaring and then adding, I'm checking out if this is total is greater than one critical. The biggest drawback which I could see is there could be very few small deviations but one large deviation. Now when I square it and add up, probably because of the squares of these numbers are very small and all this is very large, the overall summation could still be lesser than the critical value. Because this overall summation may be less than the critical value, we may say that the graduated rates are more or less, or the observed rates are more coinciding with the graduated rates. Okay, So we can see that the graduated rates are much deviated with the graduated rates. So if we look at the comparison with the overall values, the large deviations might be overlooked because of many small deviations which may be present. And the other way which could come out is the z values for all of them may be negative, small but negative. Once I take the zx squared, it may not be high about the critical, but all the individuals for the x's, they'll may be negative, they'll be positive or negative, which means it's an indication that my graduated model, whatever I'm using, if the observed minus expected are all positive, then the graduated model is undergraduated. Because the actual deaths are more than what are being estimated. But overall, this chi-square test, chi-square test is getting passed because I'm not getting rejected, because all the zx squared may not be greater than a critical value. But individually, when I'm looking at the zx's, all of them are positive or all of them are negative. This is one major drawback which cannot be covered by this chi-square test. And the other thing that could come out is there could be a lot of biasing in a lot of age groups. So there will be some negatives, then positive. So some kind of grouping in the individual data could be there in the ZX, apart from the ZX squared. See, only in the ZX squared is greater than a critical value that I'm saying that the actual data may not be, or the observed data may not be adhering to the graduated rates. Okay, but if zx squared is less than the critical value, directly I'll say that there is no evidence that I can retain that statement, so I may be forced to go with that statement itself. But what we're saying is that the three major drawbacks can occur, one of which I've already highlighted. Some large values, some large deviations may be overlooked because many other deviations are very small, or probably the entire data may be overgraduated or undergraduated, and overall sigma z squared may not be greater than the critical value. Or there could be some groups of some ages where in up to a certain group, is a negative, is undergraduating, after that is overgraduation. Again, sigma z squared is not so significant that the overall model is not coming out as not a fitment to the graduated rate. So that's where using a standardized deviation and squaring the standard deviation and comparing with the chi-square test, though it is the one of the better models to use, it has its kind of limitations, which are addressed by a few other tests which I'm going to look at them from now. So out of them, one such kind of test which I'm trying to look out for is a standard. Is that a standardized? So the next one is what? The standardized deviations test. So here my intention is to see if the large number of these deviations of larger deviations are upsetting the large number of small deviations. Large number of small, so that the overall sigma z squared is less than the critical value of the chi-square test, then there is no significant test between the observed rate and the graduated rate. So that is the main intention of using the standardized deviation test. So what we do is, whatever the zx we are computing, the zx's are nothing but their values from a standard normal distribution. So these are nothing but values from a standard normal distribution. So what I can very well do with them is, so I can split the whole typical normal distribution. So I can split -3, -2, -1, and then here I have 0, 1, 2, and 3. So you split this entire interval, minus infinity, -3, -2, 2, 1 to 0, and 0 to 1, 1 to 2, 2 to 3, 3 to infinite. So you split this entire interval into like that, into this, and you look at the actual z's which we have computed here by comparing the actual with the graduated. Try to find out how many z's are in each category, and you also know how many z's, if at all, they are coming from a normal distribution. If at all, if they are coming out from a standard normal distribution, how many z's should be there. So if you say we have 100 minus 1, so 68%. So probably I require 34%. Okay, and 0 to 1 I require 34. So yeah, so this is how you do the standardized deviations test. So we look at so now we look at what? Overgraduated or undergraduated. So this is what we're going to look at now. So look at the z-axis. It may be possible that all z-axis may be positive, or all z-axis may be negative. Each of them may be very small positive or very small negative. So I'm trying out the zx squared may be small and positive, and the summation may not be so high that it exceeds a certain value. That way the chi-square test is not able to find out or unable to test whether overall graduated rates are overgraduated or undergraduated. So to we are trying to address that particular mechanism using the science test. So look at the science test. So the next test is the science test. So in the standardized test, there are some, the science test is trying to test whether the overall graduated tests are undergraduated or overgraduated. So that's the purpose of the science test. We are trying to test out based on identifying the number of positive signs that are there in the Z. Number of positive Z-axis. Think of them to be some n, the number of positive signs that are there. Assume that there are n positive Z-axis. In the actual data, let's say I got n number of positive Z-axis, but the number of age groups that I have, let's say some m. Now the science test, what is doing, you assume that n follows a binomial distribution with m and 1 by 2. So you are looking at n as a binomial distribution with m and 1 by 2, right? And of course, we can find out the mean. What is the mean of this binomial distribution? So mean is equal to m by 2 and variance is equal to m into 1 by 2. So which is m over 4, which is the variance. So we can find out the mean and the variance for this. So if the actual observed number of positives is much lesser than the mean, if I'm making a normal assumption, 1.96 times standard deviation, or if my n is greater than mean plus 1.96, we will reject the null hypothesis. And say there is over or undergraduated. But if my n is ranging within itself, then I cannot comment on the overall or undergraduation. So this becomes a two-tailed test because I'm checking out for the deviations for the sign, for the lower side and the higher side. More positive number of z-axis, we are seeing that the actuals is greater than the expected. In the expected, the rates are much lower. So you can say that there is a lot of undergraduate rates. Similarly, when you're seeing that the number of positive are much lesser than the mean, 1.6 times the standard deviation, we can say that more of negatives are there, which means that the more of the expected are higher than the actual. So which means that there is over graduation present. So what could be done is, one, I can use the normal distribution assumption of the binomial and then go with the mean of 1 minus 1.96 standard deviation, or we can go with mean plus 1.96 standard deviation and we can test out whether it is greater than otherwise I can purely restrict myself to the binomial distribution itself, right? I can very well go with the binomial distribution itself, wherein if I want to find out the positives that are there, so So you can very well check out that this is very binomial. So for a binomial distribution is a ncx p power x 1 minus p to the power n minus x. So this is for the binomial. Okay. This is the probability for each one. So if I want to find out the probability above a particular value, so what's the probability with respect to p? But we won't be able to, this is not in your syllabus at the moment, so we are going to skip it. Yeah, anyway, so we come to the end of our session. So this is not your particular concern. So we've looked at the science test and the standardized deviations test. I'll see you in the next session I'll see you in the next session. Thank you.